Algebra 1, Lesson 25, we are looking at relations and functions and being able to figure out is a relation a function or is it just a relation? First, let's start out with some vocabulary words. If we are talking about domain, we're talking about the set of inputs or x values. Range is the set of outputs or y values. Relation, we're talking about how each number in the domain is matched to one or more number in the range. It's really just a set of ordered pairs. Whereas a function is a specific type of relation where each domain value has one and only one range value. What this looks like is that if we have relations, which is just a correspondence between two sets, really just a relationship somehow with the domain and range, functions are a subset, okay? So every function that we have is a relation, but not all of our relations are functions, okay? So we have all of our relations and some of them are functions. So for example, if we have something like y equals 4x, we can decide, all right, if I have an input for x, will it have one and only one output? And if we work through it, we can see, yeah, if I have an x value, I'm going to have one and only one y value. Okay, so that will make y equals 4x a function. Right? We could make a table of values. What this looks like is something like this. For example, we have a domain of 1, 2, 3, 4, and a range of 5, 6, 7, 8. We can see that 1 goes to 5, 2 goes to 6, 3 goes to 7, 4 goes to 8. Is this a function? And we would have to think, okay, every domain that I have can only have one range value attached to it. And we would say, yes, this is true. This is a function. One domain equals one range. Now, if I were to change this and let's say 4 goes to 7 and 4 goes to 8, we would say, no, this is just a relation. Because 4, a domain value, has 2 outputs, which is not okay. Another example, is this a function? Well, if we were to look at this and look at these pairs, we know that it's a relation because our domain fits with somehow with our ranges. But we can see, all right, we have 2, 6, 2, 10, 8, 6, 5, 1, 4, 6, and 3, 9. We want to look and see, do I have more than one input value or do I have one input value give me more than one output value? And we would say, well, the only one that could fail is that 2. And we can see, yeah, 2 gives me 6, but 2 also gives me 10, which we said was not okay. So this is not a function. Okay? We can talk about the domain saying, what are my x values? What are my input values? And we want to put them in order from least to greatest. So we would say 2, 3, 4, 5, and 8. We do not repeat the 2's that we had because we just want to say I have a 2. I don't care that I have 2 of them up there. Range, on the other hand, when we look, we're looking at our output values. So we would say we have a 1. We have a, 6 is our next one. We have a 9. And we have a 10. Okay? 1, 6, 9, and 10 are my range values. Those are my output values. So we have already determined that this is not a function, but visually we can show it's not a function because even though 3 goes to one value, 4 goes to one value, 5 goes to one value, 8 goes to one value, unfortunately 2 goes to 2 different values. So that fails. It is just a relation. It's not a function. Okay? Let's see if I'm going to make up something for this. We have our domain values of 5, 2, 8, and 6, and range values 6, 12, 15, 7, and 19. Well, I could say, all right, maybe this 5 goes to the 12, 2 goes to a 6, this 8 goes to 7, and 6 goes to 15. As it is right now, all of my domain values have one and only one output range value. But once I include that 19, maybe 6 goes to 19, we would say, no, this is not a function. It's just a relation, because 6, unfortunately, goes to 2 different things. How about this one? Is this a function? So we look at my inputs, 7, 15, 23, and 15, and we see, okay, do we have any that repeat? And we say yes, 15. Do they go to different values? And unfortunately they do. So 15 makes it fail because 15 goes to 24 and 15 goes to 19. So one input, 15, goes to two different values. So this would not be a function. So it's a relation, just a relation. Next one, determine whether 3, 3, 10, 1, 0, 3, 8, 9, 4, 4, and 10, 2 represents a function. We would say, okay, I'm going to look at my inputs, 3, 10, 0, 8, 4, and 10. And I see that, oh, no, I have a repeat, 10. And unfortunately, it goes to two different values. 10 goes to 1 right here, and 10 goes to 2. So that is not okay. We would have to say no. This is not a function because unfortunately that 10 goes to two different values. Determine whether y equals 1/2 x minus 1 represents a function. Well, we could go through and work through a table. Maybe we say, all right, if I have x values of 2, 4, 6, and 8, I plug them in. 2 times 1/2 is 1, minus 1 is 0. 4 times 1/2 is 2 minus 1, which is 1. 6 times 1/2 is 3 minus 1. And 8 times 1/2 is 4 minus 1, so we get 3. Will we ever have an input value that gives me more than one output? And the answer is no. So we say that this represents a function. No matter what value is substituted for the independent x value, the equation outputs exactly one value. So this is a function. All right. We can also determine if something is a function using the vertical line test. What this is saying is that if we have a graph on the coordinate plane, we can use a vertical line and see if it intersects the graph at one point, or if it's more than one point, then we would say that's not a function. So for example, that first one on the left, the relation is not a function because the vertical line cuts the graph in more than one place. So we can see this dotted blue line right here, and we see if we have a vertical line, it connects right there and connects right there. What we are saying is that if we have this vertical line at x equals 3, well, at x equals 3, it has a value of 3.25 about, and a value of negative 3.25, which means that we have one input value x that has more than one output value. So the vertical line test says if we can put a vertical line and it only connects in one place, then we have a function, which is what we have with our line over here. Our vertical line hits at one place. Vertical line hits at another one place. Vertical line hits at one place. So we have a function. All right. So if we have something like y equals x squared, let's see what happens. All right. Maybe we have x as negative 2. Negative 1, 0, 1, and 2. Well, negative 2, I'm going to plug these in. Y equals negative 2 squared. Well, that gives me 4. Y equals negative 1 squared. That gives me 1. I get 0, I get 1, and I get 2. And so we say, all right, is this a function? Well, we have all unique input values, and they have one and only one output value. But as you can see on, sorry, this should be a 4. On our right side, our output values, I have some ones in common, 1 and 1, 4 and 4. Is that okay? And we would say, yes, that is fine. That is fine. Okay, we can have the same output values for different inputs. It's just not okay to have the same, to have one input value having multiple output values. Because when we look at this graph on this function on a graph, it's a parabola, which will pass the vertical line test. We can put vertical lines all throughout it, and it's going to only hit in one place. All right. Even when we get up really, really high into those infinity y's, it will still be just in one place. This is a function. Now we have our relations, which inside of those we have specific ones called functions, and we can have specific types of functions, which are called one-to-one functions. What this is saying is that, just like we saw on the last page, we're allowed for a regular function to have the same output values having different inputs. With one-to-one functions, we don't allow that to happen. We want every input value, okay, let's say we have y equals 2x. We want every input value, so -2, -1, 0, 1, and 2. We're going to get -4, -2, 0. Oops, sorry. Yeah, I have it right. I think, yes. Okay, 2 and 4. We want to make sure that all of our output values have one and only one input. So we have one input gives us only one output. That gives us a function. But to be one-to-one, we have one output value gives us one and only one input value. It goes back and forth. That is a specific type of function called the one-to-one function. And we use a horizontal line test, just like we would use a vertical line test. If it hits only one place, then we're good to go. That's a one-to-one function. Okay? All right, if we look at this, we can see if we were to plot all of these points and connect them, because we have a line here, we can see that will pass the vertical line test, which means it's a function. And if we were to look at this and say, is this a one-to-one function? We would say, okay, instead of the vertical line test, I'm going to try the horizontal line test. So when we have this line, we say, okay, if I put a horizontal line, will it cross in one place? Another horizontal line, just one place. One place. So this is a one-to-one function. Okay. So we have relations, and inside of those we have functions, and certain types of functions are one-to-one. The last part of this lesson is talking about function form. What this means is that we have a way to describe our equations that we use, and we say this is function notation. The first thing that you have to do, number one thing, is get y alone. Okay? So once we get y alone, then we have one more step after that. Okay? Sorry about all of these lines, folks. Okay? So first thing we do, we get y alone. Second thing we do, we replace y with f of x, and I'll show you what this looks like. So if we start off with this equation, x plus 2y equals 5. If I'm going to get y alone, I am going to, oops, sorry about that. Let me get rid of that. Must have pressed something that I shouldn't have. Okay, so we subtract x so that we can get y by itself. All right, bear with me, folks. Sometimes my board thinks I'm trying to do too many things at once. All right, we're getting it figured out. All right, I subtract x and subtract x from the other side. Oh my goodness. All right, we're getting there. So we subtract x from the other side, and we get 2y equals 5 minus x. All right. Maybe. Good grief. I'm sorry about this. Hopefully you are staying with me. So once we do that, we still have to get y alone, and we divide by 2. We have to divide everything by 2. So that we get y equals 5 divided by 2 minus x divided by 2. So we have gotten y alone. The last part of this is to just replace y with our function notation, which is just, we are saying we have the function on x, which equals 5 over 2 minus x over 2. All we are saying is that I am going to do some function on x. That's what we do to figure out my y. So y and f of x are the same thing. If I were to do a normal table, I would say I have x, and instead of just y, I would say this is f of x, because I have done a function on x. So that if I were to say, all right, I want 2, x is 2, so I would say f of 2, I'm going to do a function on 2, and that means that I'm going to do 5 over 2 minus 2 over 2. I'm doing a function on 2, my x value, which means that I get 3 halves. I could do that again for f of 4 and say I have 5 over 2 minus 4 over 2. And so I would have 1 half. All right, so my 4 would be 1 half. F of x is just a fancy way to say y, but it's good to start thinking in this way so that when you get to Algebra 2, geometry, these function notations come in really handy when we're doing multiple equations together. So let's try these on a couple other ones. So 6x plus 2y, we're going to subtract 6x from each side, so we have 2y is equal to 16 minus 6x. We divide by 2, we get y equals 8 minus 3x. But to put this in function notation, we would say we have f of x equals 8 minus 3x. That's it. Okay, so get y alone and replace y with f of x. So if we already have y alone, like in this right one, we would just say it's f of x equals 8 minus 3x. Okay, we're doing a certain function on x. All right, so if we were to start, I'll just read this. In a function, independent variable determines the value of the dependent, right? If we put in a value for x, it will determine what we get for the dependent variable y. This means that the dependent variable is a function of the independent variable. In terms of variables, y is a function of x and can be written with the following. So if we have y equals f of x, then f of x equals 6x plus 3. We just replace y with f of x. One last example here. A student reads an average of 25 pages per day while reading a 544-page novel. Write a rule in function notation to find the number of pages she has left to read at the end of any given day. Well, if we were to say, let's just do this normally and then replace my y with function notation. So if x represents the number of days that she has read, and y represents how many pages left, we could say y equals, well, she's already read 25, so, she reads 25 per day, so we would say 25x, 25 per day, and we're taking that away from an entire novel that is 544 pages. So we'd do 544 minus 25x. Well, in function notation, all we would have to do is say f of x equals 544 minus 25x. So that we could say, all right, maybe she's read for 10 days. That would mean that we would have 544 minus 25 times 10. And we can just simplify and solve. Well, I hope this helps you understand relations and functions a little better, and I hope this has helped with your homework and for studying.